Hi students, Professor Gray here. We need to talk about electronegativity today. Now, I've switched over from PowerPoint to Notability because PowerPoint wasn't displaying the pictures for this part of the presentation. But what I've noticed happened in Notability is that the subscripts are no longer subscripts. So I think we can deal with that because the pictures are a little more important. So let's back up to the first slide in this group, which is right here, electronegativity. And electronegativity is the concept that different elements have different abilities to attract electrons to themselves. So the higher the electronegativity value, the better the atom is at attracting electrons to itself. Now, if we look down at the picture below, we can see that electronegativity increases across a period, so left to right. So we can see that lithium has a value of 1 and fluorine has a value of 4. And we can also see that electronegativity increases as we go up a group. So on this picture, potassium is 0.8 and lithium is 1.0. That means that our electronegativity values are very low in the bottom left-hand corner of the periodic table, and they are high in the top right-hand corner if we ignore the noble gases. So you can see how from potassium we go 0.8 to fluorine of 4.0. Now if we take a look at the entire periodic table, we can see francium of 0.8 and fluorine of 4.0, and it increases diagonally up. Now on this slide, we can see that francium is 0.8. And if we take a look at the next slide, which shows us exactly the same thing, just in a 3D format, we can see that francium is 0.7. Don't worry about the difference there, 0.7 or 0.8. It just means that you had some different researchers that used some different methods or calculations for these values, but they are almost identical. We can see on this chart that francium is also fluorine is also 0.4, and we still have an increase diagonally up the periodic table. And that makes sense because we know that our halogens over here, they really like to gain an electron and become an anion. And our alkali metals over here, they like to lose an electron to become a cation. So if we look back at this page, another thing you'll notice is that there's no values for the noble gases. Now remember with the noble gases, they have a complete octet, or in the case of helium, a duet, and they're happy. They don't want to gain any electrons. So that's why there's no values there. They're like, no thank you, we're not going to give away our electrons and we're not going to gain any electrons because we're completely happy. Now, electronegativity means that we have to talk about types of bonding. Now, we've talked about covalent bonding and ionic bonding, but there's a lot of in between. So let's go back to covalent bonding, and there's a couple of different ways we can classify our covalent bonds, and the first one is a nonpolar covalent bond. Now, a nonpolar covalent bond, that happens when we have a couple of atoms that are bonding to each other, and their difference in electronegativity values is not that great. So if we look at our Cl2 right here, we have two chlorines that have exactly the same electronegativity value. They're both 3. So the difference in their electronegativity values is 0. That means that one chlorine is saying, I'm really electronegative and I want to hog the electrons over towards myself, except the chlorine on the other side is like, no way, man. I have equal strength and I'm going to pull on the electrons this way. And that ends up with a tug of war where the electrons don't go in either direction. They stay nice and evenly distributed around each of those atoms there. If we have a difference in electronegativity all the way up to 0.4, we consider that to be a nonpolar covalent bond. And where we will see 0.4 is with carbon-hydrogen bonds. So if we have methane and we draw out our Lewis structure for methane, we can see that we've got 4 different bonds there, and each one we look at separately. And the electronegativity value for carbon, we're going to find that on our chart right here, and we can see that that's 2.5. And the electronegativity value for hydrogen is 2.1. So electronegativity value for carbon, 2.5, and the electronegativity value for hydrogen is 2.1. So the difference in electronegativity is 2.5 minus 2.1, and that is 0.4. And 0.4 still qualifies as a nonpolar covalent bond. So what that is saying is that in the bond between the carbon and hydrogen right there, nobody is hogging up the electrons or pulling the electrons towards itself more than the other. And if we look at this bond right here, we've got the same thing happening. And this bond, same thing happening, and this bond, same thing happening. So the electrons in this molecule are not shifted towards any of our atoms more than the other ones. So we've got nonpolar covalent bonds. We don't have poles. If we look at this molecule right here, HCl, what we'll see is that the electronegativity value for chlorine is 3.0, and again, I got that from the chart right here, 3.0, and the electronegativity value for hydrogen is 2.1. If we do the difference in electronegativity values, we'd have 3.0 minus 2.1, and that gives us 0.9. And 0.9 is greater than 0.4, so it means that the more electronegative atom is pulling the electrons in this molecule towards itself more. And how we symbolize that is with a lowercase delta symbol and the negative right here. So that looks like a funky O with a little weird hairdo there. So we say that's partially negative. And if that side of the molecule is partially negative because it's pulling the electrons, which are negatively charged, towards itself, that must make this side of the molecule partially positive. So we have poles, or we have a polar covalent bond. Now the chlorine in this molecule isn't completely stealing the electron, so it doesn't have a whole charge of -1. It just has a partial charge, and that's what that delta minus symbolizes. Now over here it says that we have a difference in electronegativity values of 0.4 to 2.0 for polar covalent bonds. Now that should say greater than 0.4 because 0.4 exactly qualifies as nonpolar. And the 2.0 on the end has a little bit of wiggle room also. So some books and some websites and some professors will say 1.8 or 1.9, and it's going to depend on which molecule we have also, which compound. But that's a general guideline for a polar covalent bond. And again, the electrons in the polar covalent bonds are not shared equally. The atom that has a higher electronegativity will pull the electrons towards itself more. And the other way that we can symbolize that we have poles is with a dipole moment. So that's down here. So what we do is we draw this little arrow that has a plus symbol on one end. So we say that the electrons are being shifted this way towards the chlorine, and that means that on this end it's positive. Now, what we do is we either draw the dipole moment or we draw the delta symbols in. We don't do both. It's one or the other. And you'll see both of them drawn equally. Another way that we can show that we have an unequal distribution of electrons is through an electrostatic potential map. So you have electrostatic potential map right here, and the red zone right here is showing that we have a higher electron density over there, and the blue zone over here is showing that we have a lower electron density. Okay, so what happens when we have a difference in electronegativity that's greater than 2.0? And again, remember there's some wiggle room on the 2.0. So sometimes we'll see a 1.8 or a 1.9. That means that one of the atoms has enough strength to completely steal an electron. Instead of sharing it unequally, it just takes it. And that happens in this example right here. We have an electronegativity value for chlorine of 3.0 and an electronegativity value for sodium of 0.9. The difference, 3.0 minus 0.9, ends up being 2.1. And that definitely qualifies this as being an ionic bond. So we have a complete transfer of an electron. So we have whole charges. We have -1 and we have +1 instead of those partial charges of the delta minus and the delta plus. Now, if you weren't listening to the last few slides, here it is in picture form, and I'm really sorry that the slide messed this up a little bit, but I'm sure you guys can see it on your own slides that a pure covalent bond over here is between 0 and 0.4, and then right in here between 0.4 and 2.0, we've got our polar covalent bonds. And then when you have a difference above 2.0, we have our ionic bond zone. So we have a complete transfer of the electron over here because our electronegative atom had great enough electronegativity compared to the other atom to steal that electron. So we have complete transfer of our electron. So let's do a couple of problems, and let's decide whether we have a nonpolar covalent bond, a polar covalent bond, or an ionic bond. Now with KBr, you guys should be able to recognize that potassium is a metal and bromine is a nonmetal, and when we named covalent and ionic compounds, we were looking for a metal to tell us that that was ionic. So this one you guys should be recognizing. That should probably be ionic. But let's go ahead and take a look at the electronegativity values for potassium and bromine and see if the difference between the two is 2.0 or greater. So let's go back to our chart because that's where we find the information. And we can see that potassium is 0.8 and our bromine is 2.8. So we have 2.8 and we have 0.8 here. Now remember, difference just means subtract. And what you guys will do is just put the bigger number first and the smaller number, subtract that from the bigger number, and you guys will get the difference there. And the difference is 2.0, so that definitely qualifies potassium bromide as ionic. Now this guy right here should be written as Br2, but again, notability is not helping me out with that, so I'll just write it again. Now bromine, we can see up here, has an electronegativity value of 2.8. But you guys should recognize right off that this is probably nonpolar covalent because you have two of the exact same atoms bonding to each other. But if we go ahead and do the difference in electronegativity values, we would have 2.8 minus 2.8 is equal to 0, and that qualifies as a nonpolar covalent bond there. Now, where did I get that information besides right here? I got it off the chart. So we already went ahead and took a look at bromine right there, and it was 2.8. All right, carbon monoxide. So carbon monoxide was this funky looking Lewis structure right here where carbon has a lone pair, and we know carbons don't usually like lone pairs, and oxygen has a triple bond in one lone pair, and oxygens tend to like two bonding pairs and two lone pairs. So that one was a little bit weird, but we only had enough electrons to write this structure and also follow the octet rule too. So the electronegativity value for carbon is 2.5, and the electronegativity value for oxygen is right here at 3.5. So again, carbon's 2.5 and oxygen's 3.5. So we have 3.5 minus 2.5, which equals what? 1. And 1 is greater than 4.0, but it's less than 2.0. So we're right here in this zone of our electrons being shared unequally. So we have a polar covalent bond. Now, how would we symbolize that on our Lewis structure? Well, we could do it one of two ways. You're going to put the delta minus sign on the atom that has the higher electronegativity, because remember, it's attracting electrons towards itself, and electrons are negatively charged. So if you're hogging a lot of the electrons, you're going to make a partial negative. And that means that we create a partial positive on that side of the molecule. So we have poles. The other way that we can symbolize this is with a dipole moment. So we would draw our positive symbol on the partially positive side of the molecule, and we would indicate a shift of our electrons over to the more highly electronegative atom. So we can symbolize it again either way, but we don't want to do both. All right, number 4. Number 4, we've got iodine bonding to fluorine. So if we were to draw the Lewis structure for this molecule, it would look like this. And the electronegativity value for fluorine, we should have that in our head already. That was the most highly electronegative atom, and that has an electronegativity value of 4.0. And the electronegativity value for iodine, if we look that up, we'd come on over here and see that we've got 2.5 there. So 2.5, so we have a difference of what? Of 1.5. So 1.5 classifies us as polar covalent. So we're right in here. We're in between 0.4 and 2.0. So it's polar covalent. Now, which side of the molecule, the fluorine on the left or the iodine on the right, is pulling the electrons towards itself more? The fluorine, because it is more highly electronegative, so it will be hogging the electrons. And if we create a partial negative on that side of the molecule, we must have created a partial positive on that side of the molecule. Now again, we can symbolize it with a dipole moment, which is a little arrow with a plus symbol on it, but we don't want to do both that and the delta symbols. So we can erase our delta symbols and draw in the dipole moment if we prefer the arrow. Now, which way does the arrow point? Towards the fluorine or towards the iodine? Towards the fluorine, that's right. Because the fluorine is more highly electronegative, so it is better at pulling the electrons towards itself. Now, if we had drawn the Lewis structure the other way, which you can, that's correct also, what we would do is we would still point the arrow towards the more highly electronegative atom, which is still the fluorine. So the dipole moment would go that way if you had drawn the molecule that way. So again, this one is polar covalent. Okay, so that is electronegativity. And in the next lecture, we're going to get to VSEPR theory, which is valence shell electron pair repulsion, and we're going to talk about the geometry of molecules. And then we're going to put the electronegativities together with geometries, and we are going to take a look at molecular polarity. But that's next time. So see you guys then.